Hello, welcome to my channel. In this video, we are going to be solving problem under Bessel's differential equation. First, we will try to see the differential equation called the Bessel's equation and also solve it using the series solution method. So, we have the equation given as this. Right, we have d squared y dx squared plus 1 over x dy dx plus 1 minus n squared all over n x squared into bracket y equal to 0. Our n here is a constant. So this differential equation is a second order differential equation, and it can also be represented in a compact form as y prime prime and plus 1 over x y prime, where y prime prime represents d squared y dx squared, y prime dy dx, and so on. Now, to solve this problem, it's important for us to know that functions in mathematics can be represented in the form of series. Just like you have sin x can be represented in the form of Taylor series, can be expanded in the form of Taylor series. So likewise, we can represent the solution of this Bessel's differential equation in the form of series. So we start by assuming that the solution to this expression, which is y, can be expanded in the form of series, which is giving us y equal to this expression. And if we expand this expression, it is giving us a naught xk plus a1 xk plus 1. That's following our r running from 0 to infinity. We also have a2 x down to infinity. So our aim in this problem is to determine the value of a naught, a1, a2, all the constants, and also the value k, because k is a constant also. Our r here runs from 0 to 1, so it's not a constant. Now, to determine this expression, it's important for us to know that we can also substitute this expression back into this expression, this original equation. And since we know that our y is this expression, which is this, we also need our y prime, which is differentiating this expression with respect to x once. Then we also have y prime prime, which is differentiating this expression with respect to x twice. So let's see. If we differentiate this expression with respect to x once, we have y prime equal to this k plus r. We go back. Just like you differentiate x, we have k plus r minus 1. If we differentiate the second time, because of this one, we get y prime prime equal to this one. We go back. We multiply the x, which is k plus r minus 1, then x raised by k plus r minus 2. Now we can substitute this, and this into this equation to get this expression. Now that we have this expression, we notice that we can resimplify by bringing out this summation to the left-hand parts, and AR is common. We can bring them forward to the right-hand side so that we have this expression in a simpler form. We have summation here and AR. Now we can deal with this one by taking x to meet this one, and x squared, we can expound this one. X squared here will meet this one will meet this one, so that we have an expression of this form. So we have these two with this. X will make this one reduce to minus 2. Then we have 1 times this will give us this. This minus this expression times this will give us this expression, which will reduce this one to minus 2 also. From this point, we can factorize our x, which is raised by k plus r minus 2, is the same here and is the same here. We can bring them together to give us this expression. So at this point, we can concentrate on these parts by simplifying this. And what you notice is that this k plus r and k plus r can be factorized out, leaving k plus r minus 1 plus 1 after factorizing this one out. So that plus 1 will take care of this minus 1, and we have k plus r into bracket k plus r minus n squared and this expression. So at this point, we can simplify this one by saying k plus r squared, and we have k plus r squared. So at this point, right, we have k plus r minus 2, which is the power of x of this one is lower than this one. Because it is minus 2, we want to get to the initial equation. And in this initial equation will help us to determine the value of a naught, the value of k, and the value of a1, right? So to do that, we first of all get one of the points at this point equation, which is a naught, right? And when we substitute the value of a naught, we'll see what we can get. And that's the fact that if we recall, our expression is y equal to this expansion. Take note, this is part of the solution of y. If you notice, our x here has k, x here has k minus plus 1, then x here has k plus 2. So all the powers of x here are all positive. None is negative. So if we have any negative anywhere, we'll know that that one does not exist. So take note of these parts. Because we have minus 2, we will find the points a naught and a1. If here were to be minus 3, we'll find a naught, a1, and a2. If here were to be minus 1, we'll find a naught alone. Exactly. So let's go and find out the points at which we have a naught in this equation and a1. So we have a naught. Wherever you see your r, you represent with 0. So all our r in this equation, they are all now 0. So at this point, if we expand this by this, we have a naught multiplying this, a naught multiplying this. So if you recall that we said that x raised by k minus 2 cannot be found in that solution because it is negative. But this one can be found in the solution. So what does that mean? It means that the coefficients of this expression, which is a naught times this, must be equal to 0 because this one is not part of the solution. So we can conclude that k squared minus n squared multiplied by a naught must be equal to 0. Now, if we have this term and this term multiplying and it is equal to 0, it therefore means that one of these terms must be equal to 0. And because a naught is part of our solution, we cannot just make it 0. So we conclude that this part will be equal to 0. And we get k squared minus n squared equal to 0. Then we can make our k the survey formula, which is plus or minus n. So we have two values for k. So just by representing a naught, which is one of the term in that expansion, which is this term, we're able to find k equal to plus or minus n. So we'll now go back to this expression again and see wherever we see r, we'll represent by what? We'll represent r by 1 to get the second term. So we have a1, we have r equal to 1 here, r equal to minus 1, then r equal to plus 1 here. So at this point, if we expand a1 times this, we get this expression, right, which is the next second term of the expansion. So we notice that this expression for x k minus 1 cannot be found in the solution 2, but this one can be found because they are all positive term, this power of x. So what does that mean? It means therefore that a1 times this expression will definitely be equal to 0 because it does not exist in the solution. So we have this one minus n, a1 equal to 0. Now again, we are meeting this expansion. This times this equal to 0. And at this point, we can now see one of them must be equal to 0. And you might be tempted to say that this part will be equal to 0. But that's not so. That's not true. Because we have already found our k to be n plus or minus n. So if you substitute the plus n here, you notice that we have n plus 1 squared minus n squared. You can see that this part can never be equal to 0. It's either it is greater than 0 or less than 0, not equal to 0. Why? Because our k here is already n. N plus 1 is either greater than n squared or less than. That's if you substitute the minus n. At this point, we can now conclude that a1 must be equal to 0. And we have a1 equal to 0. So if that's the case, we go back to the original equation. So we recall that this expansion is equal to 0. So from this expansion, because this one is minus 2, remember we substitute a naught and a1. If it were to be 1, we just get for A naught. But now it is minus 2. We got A naught and A1. If it were to be minus 3, we will need to solve for A naught, A1, and A2. Okay, so at this point, we want to get our recurrent relation. And to get our recurrent relation, we need to substitute, or we need to make this particular power equal to this, right? So that they can be the same. And to make this one exactly equal to this, we just replace our r with r plus 2. So anywhere we see our r in this expression, we'll replace with r plus 2. And we'll get r plus 2 from this point. Then r plus 2 will give us this and this. Now we now have this one equal to this. If here were to be minus 1, we just replace r with what? R plus 1. So that this part will be exactly equal to this. So if we factorize this and this out, you notice that this term xk plus r is almost the nth term or the rth term. And the rth term in any series, as you go further the series, the coefficients of xk plus r, which is the rth term, tends to be smaller, tends to 0, right? So if we factorize this out, the coefficients ar plus this and this will definitely be equal to 0, because as you move away from any series, the coefficients of x raised power k plus r will definitely tend to 0. So we have this expression. So we now have k plus r plus 2, ar plus 2 plus ar, which is the coefficients of x, k plus r equal to 0. So at this point, we can make ar plus 2, a subscript r plus 2, the subject formula, to get our recurrent relation, and hence we get this expression. So at this point, we can simplify this one further, because we can say it's a difference of 2 squares, and we have this expansion. So it will be this, what is inside here, minus this, what is inside here, plus n, which is what we have here. We can go a step further by saying we already know our k, right? So for k equal to n, let's solve for k equal to n, because we have k equal to n and k equal to minus n. So we move further by one step. For k equal to n, we have this expansion. So wherever I see your n, k, you represent with n, and that takes care of this one, which reduces to this. N plus n will give us 2n. So at this point, if we know here to be a naught, this one will give us a2. If we know here to be a1, here will give us a3. If we know here to be a2, here will give us a4. That's the recurrent relation. So for a1, here will be a3. And we have already established that a1 is equal to a3. A1 is equal to 0. So, and if here is a3, that means we can say our a1, which is equal to 0, is equal to a3, which is equal to a5. All the odd numbers will be equal to 0. So we are left with the even number. So if we recall, so we have our a2 equal to minus a naught equal to this expression. If we substitute a naught, what about our a2? If we put 2 here, here will be a4. So we have a4 equal to this expression. But we already know our a2 to be this expansion. So we substitute it here. And recall, we have here is supposed to be minus. So for a4, we have a4 equal to minus 1. There's a mistake here. We're supposed to have minus. We have the minus 1, then minus a naught, right? So it's like we're substituting this one as h2, which is this, into this one. So we'll end up with a4 equal to this. So we can use this same idea to determine what a6 will be, which is this expansion, right? So if we recall that our expansion is this expression, we already know that our a1 is 0, a3 is 0, and we already know our k is n. So we have k equal to n, a naught, a1, a2. So our a1, a3 is equal to 0. So this expansion will reduce to a naught, a2, a4, a6, a8, down to infinity, right? Now that we know our a naught, a2, a4, and a6, and so on, we can substitute them in to get this expansion. So this one is for A2, x n plus 2. This is for A4. So we can stop at this point and say from this point, what we notice is that A naught x raised by n is common to all terms. So if we factorize A naught xn out, we'll get A naught xn. Here we'll be left with 1 minus x squared all over this expansion plus x4 all over this expansion minus 1 and so forth. Now we can generalize this term by using a summation time and re-express it in terms of the nth term or the rth term, and that gives us A naught xn summation of this expansion. So if you notice, this one represents the rth term. So we can see that from here, if r is 0, r is 0, r is 0, r is 0, we end up having here to be 1. If here is 1, r is 1, r is 1, we end up having this particular term. Now, how did we get this term? If you notice, there is 2 here, there is 2 here. We can factorize 2 out from this point. 2 will come out, 2 will come out. We are left with 1.2. So that 2 that is here and 2 that is here will be 2 raised power 2, which is 2 raised power r. We are left with 1.2, which is r factorial. Then for this expansion, we can factorize our 2 out, which is 2 raised power r, because of this expansion, 2 raised power r. Then we are left with n plus 1, which is n plus 1, n plus 2, n plus 3, n plus down to r, so which is this term. So that's how this expansion, this term is gotten. So at this point, we move on to the next case by saying, if we assume that our A naught, which is this, is equal to this expansion. This is an assumption made by Bessel. So he assumed that A naught equal to this expansion. So if we substitute it back into this expression, we'll get xn all over 2 raised by n gamma n plus 1. Our gamma n plus 1 here is the same thing as n factorial from gamma function. You can check my previous video on gamma function. So multiply by this expansion. So if we simplify this one, we notice that our x raised by n here will meet this one to become x raised by 2r plus n. This is 2n. Meeting this one will give us 2 raised power 2r plus n also. Gamma n meeting this one will simplify to this expression. Our r factorial is still here. Our gamma n plus 1 plus n. Remember, n plus 1 down to n plus r is same thing as n plus r factorial. So everything here will give us this part here. So we move on to the next stage, which is saying that expansion, let's go back, that this expansion here will give us n plus r factorial. Take note, this one, if you simplify this one alone, it's saying n plus 1, n plus times n plus 2 times n plus 3, right? So this one starts from n plus 1 down to n plus r term. But this one starts with n factorial because everything here is n factorial. And n factorial is the same thing as 1 times 2 times 3 times 4 down to n. So if you notice, this one starts from 1 to n. This one starts from n plus 1 to n plus rth term. So the combination of this one will give us n plus r factorial. So that's how we have that expansion reducing to this term. So from this term, we can resimplify, can be represented as gamma n plus r plus 1, if you remember gamma function. So at this point, we can say that this expansion is now the Bessel's function, which is represented as j of n of x, which is this. Remember, if this is j of n, when n is plus n, we can represent this one, we can rewrite this one in terms of j minus n, which is the second solution to this expression. So wherever we see n, we replace with what? N minus n, and we have j minus n, and minus n. This is the second solution. We don't have to solve it again. We just look at this and replace n with minus n. So our final solution will now be the combination of these two, which is y equal to a g of n plus b g of n. I hope this helps. Please like, share, and subscribe to my channel. Thank you.